So yeah, today I'm going to tell you about some of the research we've been doing about building machine learning systems in contexts where we don't have much labeled data or we don't have any labeled data at all. So in the past few years, we've seen a lot of progress in machine learning on a range of exciting tasks like classifying images, detecting objects in images, speech recognition, even playing Go. If you've seen AlphaGo, the system managed to beat one of the best human players in the world. And a lot of the successes were based on supervised learning models, where the idea is that you have a complex task that you want to solve, and what you can do is you can set up some model, and you can try to train it to solve the task that you care about by showing a lot of examples. So if you want to teach a machine how to classify images, what you can do is you can show a lot of examples of what cats and dogs look like, and then you can sort of see what kind of mistakes the model makes, and then you can kind of tune the parameters of your model until the answers improve and you get good results. The challenge is that in order for this to work, you typically need a lot of data. If you look here, some images from ImageNet, you see that there is a lot of variety. Images are very high dimensional, there is a lot of variability. So if you want to train a system to, say, detect different types of objects in images, you're going to need to show a lot of labeled examples. So a lot of examples of how a cat or a dog looks like. And this is okay in many domains, but ideally we would like to, it's also expensive. Labeling is costly, and it can significantly delay the deployment of machine learning systems to new domains. So a key question that also Percy alluded before is, what can you do if you don't have labels? What can you do if you only have raw digital data without any label? We all know that our sensing capabilities are getting better and better. We are collecting lots of data in digital form, but we don't have labels. So is there something that we can do in those contexts? Say, for example, I give you a lot of photos of celebrities, but I don't give you any labels. I don't tell you who these persons are. I don't tell you if they're male or female. I don't tell you anything about it. Is there something that we can do with this kind of data? And one basic way to sort of try to understand the structure of these images is to try to construct a probabilistic model for this data. So the idea is that we're going to try to build a probability distribution over images such that it gives high probability to images that look like human faces, and it will give low probabilities to images that don't look like human faces. So that the idea is that, for example, if you sample from this probability distribution, you're going to get an image that look like these ones. Or you can use these kind of models to do all sort of things. You can use them to do unsupervised feature learning. You can use them to denoise images. You can use them to do in-painting. If you only have a piece of the image, you can sort of try to complete it. There are all sort of interesting things you can do if you can construct this kind of models. So a natural way to approach the problem and try to construct this kind of models is to use latent variable models. So the idea is that there is going to be an image, which is what we get to see. And the assumption is that this image is generated by a process where there are some kind of hidden variables that capture all the latent factors of variation in an image. Like it might be the ethnicity of a person, the hair color, the eye color, the gender, the pose, and many more. And sort of there is this generative process where basically first you start by choosing these hidden variables, and then you construct the image that correspond to those hidden variables that you don't get to see. So this is the structure. And it's been quite successful at learning probabilistic models of complex data distributions. So let's see how this kind of, let me show you some examples of the kind of models that you can construct for the previous data set using this kind of latent variable structure. So here are some images. How many of you think that these images are real? Are these images real? Yeah. Some people think are real. How many of you think that, say, half and half are real, half are computer generated? A few of them. How many of you think they are all computer generated? A few of them. Okay. So what about these ones? How many of you think that these images are real? Few. How many of you think half and half? How many of you think these ones are all real? Nobody? All right. Turns out that these images, so the previous ones, these are all fake. These are all generated by a model. These ones are actually the real images that basically we can, the closest real images that we can find to the one generated by the model. So we can do a pretty good job at generating realistically looking images. And here, I cheated a bit. The model is not actually generating images from scratch. So we're not just sampling from that probability distribution, but I'm giving a little bit of advice to the model. I'm actually giving to the model the portion of the image corresponding to the eyes. And then I'm asking the model to fill out the rest of the image. So say in this case, I give this part of the image, the eyes, and then it can try to complete it. And one of them is the true image that I got from the data set. The other one is a sample. And in this case, it turns out that I believe this one is the sample, this one is the true image. So these kind of models can do pretty well. At least I've been able to fool a few of you, not all of them, but it's doing reasonably well. The challenge is that how do we actually train these kind of models? And the typical way these models are trained is that we want to, the key problem is that when we don't get to see all these latent variables, right? The only thing you get to see in your data set are the images. And so when you can construct these very complicated models with lots of parameters that describe these probability distributions. The problem is that when you train them, we don't get to see all these latent variables. So when you try to fit these models to data and find the parameters that maximize the likelihood of the observed data, of the images, you have to marginalize, you have to integrate out all these latent factors of variation. And that's a difficult problem computationally. Because if you have, say, 100 binary latent variables, you have to basically compute a sum over 2 to the 100 possible assignments to these latent variables, which is computationally expensive. So how these models are typically trained using some kind of approximations. The idea is that we can rewrite this marginal log likelihood in the following way by multiplying and dividing by some function q. And then you can apply basically Jensen's inequality, and you can get a lower bound to the quantity you care about. So this is the quantity we care about. This is a lower bound that you can get easily. And the trick is that we can choose this distribution q to be simple so that we can evaluate this lower bound efficiently. And so the picture is like this. There is a true marginal likelihood of the data with respect to your model. This is the thing you want to optimize if you want to try to put as much probability as possible on images that look on the actual training data, so true faces. But that's hard to compute, and so instead, we can define this lower bound shown in red, and you can try to optimize for that. So ideally, you would want to find the optimum, the maximum of the black curve. You cannot really do it, so instead, you're going to optimize the red curve, and you're going to hope that that will do well. The challenge is that how far apart are these two curves? It turns out that that depends on the KL divergence between this probability distribution Q that you're free to choose any way you want, and the true posterior distribution over the hidden variables given the observed ones. So the bound will be tight or loose depending on how well this distribution Q approximates the true posterior P. So this is the typical approach to learn these models. The idea is that we want to make this bound as tight as possible. So we're going to solve a variational problem. We're going to say, well, there is a true posterior distribution, which is complex, is generally intractable. We're going to define a family of simple distributions Q, and we're going to sort of try to find the one that is as close as possible to P, so that we can get the best bound. But in general, so this is the tractable distribution, it is as close as possible to P. The problem is that in general, you cannot bound this distance. This distance can be arbitrarily large. If your distribution is too simple, say it's maybe a Gaussian, and your true intractable model is maybe a mixture of two Gaussians. You cannot approximate well, and no matter how well you choose your parameters. So that's the general problem that we have in these kind of approaches. So one of the things we recently did is we introduced a new method to learn this kind of models and do variational inference, which is based on the use of random projections. So the idea is that we introduced this concept of a random projection on probability distributions, where we can effectively take a probability distribution and generate a new one, such that the properties of P are preserved to some extent, but the new distribution P prime is simpler than the original one, and so it's easier to approximate. So the scheme that we are using is the following. We basically start by taking a random projection of the original model, and then we take an I projection. Then we basically find the best approximation for this randomly projected model. And because the randomly projected model is simpler and it's easier to approximate, you can actually show that if you repeat this process a small number of times, you can get a provably good approximation of the original model with high probability, as opposed to what we had before. So before, you could not bound this distance, but if you add this random projection step, then you can get much better estimates. So you can get, so the picture basically ends up looking like this. Before, so there is this black curve that is the one that you really want to optimize if you want to fit your model to the data. You cannot really compute it, so people typically optimize this red curve, which might be arbitrarily far. And so this approach lets you define another curve, which is green, and is guaranteed to sort of be close to the black one. So if you optimize for the green one, you're actually doing a reasonably good job, because you're going to also essentially be optimizing the black one.
Can you still compute the KL divergence then with P prime?
You can compute the, yeah, P prime is simple, yeah. So you can basically prove that the KL divergence between, oh, the question is whether I can still compute the KL divergence with respect to P prime. Yeah, so yes, you can compute the KL divergence. You can actually prove that the KL divergence between the best approximating distribution and P prime is small. And then because the random projection preserves the properties of P, then you can essentially rescale things, and you can get information about the original distribution P. So this turns out to work much better. You can also combine it with these deep generative models. You can use neural networks to define the generative procedure. You can use neural networks to define the approximating families, and it does provide pretty good results in practice. So, how am I doing with time?
7 minutes.
Okay. What else can you do if you don't have labels? So suppose I have a video and I want to build an object tracker. So my student here is throwing a cushion in the air, and let's assume that I want to build train a convolutional neural network to track this object as it's moving through the air. Now, I don't have any labels. The only thing I have is a bunch of videos showing these objects moving in the air. Is there anything I can do in this context? Well, even though we don't know the height or the position of this cushion in each frame, one thing we know is that there is some basic laws of physics that the trajectory that the cushion follows in the air must satisfy. In particular, we know that the height as a function of time will form a parabola. This is just basic sort of Newton's law. There's a constant acceleration, and that will be the trajectory. So we can try to use this information to provide supervision to the system. So one thing we can try to do is we can try to construct our convolutional neural network that will take as input an image and will output, say, the height of the cushion in that image. Even though we don't have any labels, so you cannot train it by just saying, okay, this is the height, try to set the weights so that it matches whatever the training data. What we can try to do is we can try to say, well, we know we have this prior knowledge about the physics of the system. We know that even though we don't know the outputs, we know that they have to form a parabola. So we can try to use this supervision to actually train a system to solve this task. And it turns out, of course, this is not providing, it only provides, like it does not provide the whole information about the solution. It's a necessary but not a sufficient condition. But it turns out that if you add some regularization, that will basically try to encourage a solution to have a high entropy. It turns out that you can actually train a system to solve this task without any labels. So here I'm showing some results on a video that was not previously seen by the system. And you can see that it's actually able to track the height of the cushion over time fairly well, and it was trained without providing labels. The same approach can also be applied to other domains. Here we try to track the position of a person walking in the video. Again, we don't want to provide any labels, but we're going to make the assumption that the person is moving at constant speed. And of course, it's tricky to train this thing because you can imagine that the network might always output like a constant 0. It might be like it's underdetermined in some sense. It might track a pixel that never moves and output 0, and that's a valid solution based on the constraints that we impose. Then again, if you add some regularization and you put some, you encourage a high entropy solution, it turns out that you can actually make it work quite well. So you can sort of shift the burden from actually labeling tons of data to kind of engineer the right objective function by providing the right incentives when you train your models so that you can actually get the solution that you want.
So is that problem specific then? Because physics is different for evolve?
It is problem specific, so it doesn't solve, of course. The question is it problem specific? Yes, it is problem specific. The idea being that you are basically shifting the burden from collecting maybe 1 million labels for your particular problem to engineering a cost function.
So within a problem, so I assume that the physics is put into the loss function is the objective somehow, right?
Yes. The question, the physics is put into the objective function somehow. Yes.
Yeah, so, but each example might have different physics.
So clearly, yes, to some extent, but one thing, say an object moving, in this case, at constant speed, it doesn't matter whether it's a person or it's a car, it would still work. But then, the physics might be different in different applications, and so there is still going to be some effort in sort of providing the supervision. It's just a different way to do it. Instead of providing labels, you're sort of trying to provide this kind of supervision. Well, if the speed is constant or the approximation is reasonably, can reasonably be approximated as a constant speed for the bird, then I think it would work quite well. Yeah.
Is that just a function of the environmental factors like kind of camera that you use and because there is also an element of phase perception?
Yes, I'm hiding some of the details. The question is whether the camera angle and the geometry of the camera matters. And there is indeed some, you have to be careful about that. Like everything is obtained up to basically what you can tell from the image. Like there are, you don't know the depth effectively. So everything is recovered up to the depth because of course you don't know that. All right, 1 minute, moving on very quickly to, well, of course, what you can do is you can use these techniques in addition with labeled data. You can, if you have a small amount of labeled data, you can sort of try to get better results by using this kind of prior knowledge or these kind of techniques. One domain that I'm very interested in that Percy mentioned is trying to use AI techniques for social good and try to solve the big sustainability problems of our times. This, in particular, in this case, we looked at poverty. That's the #1 goal on the UN Sustainable Development Goal list. It turns out that we have very limited data about poverty. This is showing how, in the past decade, many African countries did not conduct any single survey. And so it's very hard to track progress towards ending extreme poverty if you don't have any data. So one of the things we tried to do was to see whether we can use all these new high-resolution satellite images that many startups and government organizations are providing, to see whether we can extract some kind of information about socioeconomic outcomes just by looking at these satellite images. So what we did is we tried to build a neural network that essentially tracks and predicts poverty estimates by looking at the corresponding high-resolution satellite images for that location. It turns out that we don't have much data in this case, so we had to use these kind of techniques to bootstrap the learning process. In this case, the prior knowledge we have is that the outcomes that we care about change smoothly over space and time. So you can, again, encode it into the system using a Gaussian process. Here I'm running out of time, so I'm going to go quickly on how this works. But the idea is that you can train a model that will, even with a few hundred data points, you can train a model that will look for interesting features like roads, waters, buildings, even swimming pools, farmland. And then you can use these features to predict poverty outcomes for the few data points that we have. It does very well, and it's very scalable. Like, you can run it on entire countries, and you can produce these high-resolution poverty maps that it was just not possible before because we have satellite images for basically every corner of the world. And, well, I think I'm running out of time, so I'm skipping this. But it's very accurate, and a lot of our partners are using these maps right now because, yeah, essentially there's no data, so this can be extremely useful. So to conclude, learning with limited supervision is sometimes possible. It requires new algorithms, new models. We in the group, in the Stanford ML group, we're working a lot on these kind of problems, and so there is a lot more we can do. It's a huge resource, all this unlabeled data that is available out there, and can really enable a lot of new exciting ML applications.
Thank you. Many of you had a chance to learn about that last project on using satellite images to measure poverty in the poster by Neil Jean last night. So hopefully some of you had a chance to see that. Why don't we have the next speaker come up and get set up, and while we're doing that, why don't we have one question for Stefano, because I believe you won't be available for the panel discussion at the end. So we have time for one question for Stefano.
The question I have is, how much complexity can the algorithm actually digest? I mean, I'm in dull gray insurance. So one problem we have are natural catastrophes, and being able real time to estimate what the impact of the catastrophe is going to be. Okay? If we know that the impact is going to be horrible, we can sell off that risk to the market. If we see that the expected losses are maybe low or maybe nothing, then we can retain that risk and earn good money. So now there's a lot of historical data, and there's even more and more data because we have all those sensors everywhere around in the world. But the complexity of what is happening is huge.
Yeah.
Now, we don't have celebrities to recognize. We have just ugly bunches of data that needs to be interpreted in a way that a normal human cannot potentially do. So, do you see those algorithms being able one day to digest that complexity? How far are we from it?
Well, I think it depends a lot on the particular domain, but I think you alluded a little bit to anomaly detection, kind of, like trying to figure out if something anomalous is going on. And these kind of probabilistic models are very good at that, because if you have a probability distribution over the outcomes that you care about, you can sort of figure out if something strange is happening. In fact, we've been playing with that kind of idea in the satellite images case. We're trying to build these kind of models without using any data, and we want to see whether, is there something strange going on in the world. So if you have images coming in every day, you can potentially sort of track the health of the planet sort of in real time. And so of course, it's, you need computers to do that. It's just not, the scale is huge. And so we are actually working on those kind of problems in that particular domain.